So we continue with the next part, which is NK, or ranked enumeration. So the term NK comes from anytime algorithms that improve the quality of the results as they go, and for top K, which is a paradigm that has been explored a lot for joint queries. And the idea, let me remind you again, is that we want to see the top result, the top answers very early. So basically, we are interested in the time to K, as we said, and also special cases of that are the time to the first result, also the time to the last result. So an NK algorithm starts returning results very early in the order of a ranking function. For the rest, let's assume that this ranking function is a sum of weights. And so it finds the best one very early, and then the next ones follow in quick succession. And importantly, compared to top K, the value of K doesn't need to be set in advance, so there's no hard limit to when we stop the algorithm. As a warm-up, let's look at something that's related, which is incremental sorting of numbers. So instead of query answers, let's look at simply a set of numbers. And how can we sort them incrementally? Well, if we want to sort them, we need to look, even to find the best one, we need to look at each number at least once. So if we have n numbers, we need order n to look at its number once. And to return k number sorted, we need k log k. So n plus k log k is the best we can hope for. There's nothing better than that. And you might be thinking, okay, there's a simple way to do it. Heap sort, let's build a heap in linear time, and then we pop from the heap n times. And indeed, this achieves this guarantee. But a fact that's often underappreciated is that we can also make quicksort have this incremental behavior. And there is an algorithm called Incremental Quicksort, or IQS. So let's quickly remember what quicksort does. For quicksort, we have an array of numbers, we pick a pivot, and then we partition the array into though 51 here is the pivot, and we partition to those that are less than 51 and greater than 51, and we keep doing the same thing recursively until we sort the array. Now, this sorts the array in n log n time, but now let's think, how can we modify this in order to get the top results faster? And the idea is the following, that we pick pivots as before, but only on the left side. And when we reach the bottom, we know that from the way we partition, that this element on the left has to be the smallest element. So we can return it, and we can also enumerate whatever has been sorted so far. When we are done with this, we continue with quicksort as usual, because we remember the pivots that we descended here. So we go back, and we continue partitioning with pivots as quicksort does. And we can prove that this gives us the nice guarantee of n plus k log k. Now, if you look at this, at some point after we enumerate the left half of the array, basically we will have to go back all the way to the beginning and go to the second, to the right subarray, which has size n over 2. So when we do that, the delay is going to be linear. And so the delay of this algorithm is linear, but is that a bad thing? Well, as we saw before, for any algorithm that has a nice time to k guarantee, but not a good delay guarantee, we can essentially buffer the results and return them later to make the delay uniform. So here we can play the same trick, and we can get an algorithm that has linear preprocessing and logarithmic delay. But of course, this makes the algorithm slower because we don't return the results as fast as we can. So basically, again, to remind you that low delay doesn't necessarily mean that we get a faster algorithm. And if we are interested in getting the results as fast as possible, the time to k is the correct measure to look at. So now let's try to apply the same thing for joins. So here's an example where we have 3 relations, and every relation has a weight column, and these relations join. Here are y joins with sy, sz joins with tz, and in total we have 24 results. So now, according to the weights, we want to do this enumeration where we find the best, the rank 1 result, as fast as possible, according to the sum of weights, and then we continue the second best one, third best one, and so on. That's what we want to do, and in order to achieve this, we start with the factorized representation that we talked about in the previous parts, and we apply dynamic programming on the factorized representation, as Wolfgang basically explained, and then we add this Anyk functionality on top of it. So after going bottom up with dynamic programming, we go top down, prioritizing the results that are better according to the ranking function. So for the example that I showed you before, here's the factorized representation. Recall that this is a tuple level factorization. So basically every node represents a tuple. And so we have these layers of nodes that represent tuples of relations R, S, and T. And we have also these intermediate nodes that do the factorization. And here, for simplicity, I have replaced the labels of the nodes with their weights so that we can keep track of them. And now, on this factorized representation, we can do dynamic programming. This means we go bottom up as before, and we compute the optimal weight per node. And as Wolfgang explained, this can be seen as a shortest path calculation here. So if we imagine that there is a source node in the beginning and a target node at the end, this dynamic programming computation is essentially a shortest path calculation. And now, to find the next best one, basically we have to find the second best solution to a dynamic programming problem. And with this particular representation, it's the second shortest path in the graph. So essentially, we will be looking at algorithms that can do Anyk for dynamic programming. Essentially, these are algorithms that do K shortest path enumeration. And there are 2 algorithms that are the product of long lines of research. The first one is called Anyk-Part, the other one is called Anyk-Rec. The first one works by partitioning the solution space in a particular way. And in general, it wins when the value of K is rather small. The guarantee that it achieves is basically, if N here is the size of the data and L is the size of the query, it needs N times L is essentially the size of the database. And then for every result K, we pay a log K plus L, which is the size of the output tuple. So that's what Anyk-Part achieves. Anyk-Rec, its guarantee, if you look at it, it's a bit weaker because the enumeration part can be more expensive, but it works in a way that can reuse computation. It can reuse comparisons between suffixes, essentially. And what we found is that this algorithm wins in general when the value of K is large. That's something we saw experimentally, and then we were also able to prove it in certain cases. So basically, if you have a Cartesian product, which is a rather extreme case, but that's to make the proof work, we can prove that this algorithm is faster asymptotically than sorting, which can be surprising. And so there is now this difference between the 2 algorithms. One is better for small k, the other one is better for large k. And recently, we were able to come up with an algorithm that combines the best of both of them. Basically, it extends the Anyk-Part algorithm. It's called Anyk-Part Plus, and it also has this property that it reuses computation similarly to Anyk-Rec, and it achieves the best of both worlds. So it wins over the recursive one when the K is small, and it wins over the part one when K is large. And the guarantee that achieves for time to K is dominates both the other 2. So let's see how these, in more detail, how these algorithms work. We start with the first one, which is Anyk-Part. And for this algorithm, the first ingredient that we need is the Lawler-Murty procedure. So that's a very generic procedure that basically takes a problem and it can give you ranked enumeration. It applies to many different problems. Abstractly, we have some variables that take certain values, and if we know what the best solution here is, the Lawler-Murty procedure tells us how we can find the second best one. To do that, it creates disjoint subspaces. So that is subspaces of the solution space that contain different solutions. And it says every subspace has some inclusion and exclusion constraints, and it says basically solve its subspace and then compare them, and that's how you find the next best one. So let's see how that looks like for our example. We saw that the top one query answer is essentially the shortest path in this representation. And so what is the second best one here? Well, there are only three options. Either we will deviate in the first relation, which means that we will pick a different tuple, or we will keep the first one but deviate in the second one, or we will keep both the first two and deviate in the third one. Also notice here, I'm not really concerned about the intermediate nodes. I will be mostly ignoring them because they are just intermediate stations. They don't play any role here. So basically, we have these three options, and each option is a different subspace. So the Lawler-Murty procedure says solve each one. To solve it, we solve the top one problem, which we already know how to do, and we find the weight of the best one. So to find the second best one, we compare them and we find the winner. The only thing that's left is basically how to compute this top one here. Now, and of course, to continue to go to the third best one, then the winner has to be partitioned further, and we just follow the same procedure iteratively. Now, to solve the top one, there is a default way to do it, and the default way is to say, okay, these nodes have to be deleted, so I'll just remove them from the graph, and I will just run the dynamic programming algorithm again, and this will give me the top one solution. Now, this will take linear time, n times L, for every time you do it. And so it gives basically a linear delay in every iteration. And that's actually the first algorithm that was proposed for ranked enumeration of conjunctive queries. And it's possible to do better than this algorithm. But I should mention that with projections, it's if the query is not free connex, which are basically the nice projections that we can handle, this query is the best known algorithm. It has linear preprocessing and linear delay, and it's the best that's known. So how can we improve over it for free connex queries? Well, we don't have projections here. We need a second ingredient, which is the deviations. Deviations is a concept that was proposed as early as '59 by Hoffman and Pavli, and it says the following: a deviation is a path that is the same as another path, but at some point you take some deviating edge, and then you continue optimally to the target. Optimally means exactly how dynamic programming would go, essentially the shortest path. Now, what Hoffman and Pavli proved is that the kth shortest path is a deviation of one of the top k-1 shortest paths. So if you have already enumerated k-1, you have to take their deviations, and one of those deviations has to be the next one. So that's what we use in order to solve the top one problem efficiently. Basically, whenever we make a deviation here, let's say at relation S, all we have to do is compare the optimal weights of dynamic programming to find what we call the successor. That's basically the next best deviation at this particular stage. And after we pick this deviation, then we just expand optimally in the same way dynamic programming does. Now, to find the successor, there are many ways you can do it. You can actually do it with what we said in the beginning, with incremental quicksort, and there are some other variants. And we had explored some of these variants in an earlier paper. But here, let's assume that the successor is known, that you can find it efficiently. And let's look at an end-to-end example of how this works. So we start with the graph, and we have a priority queue. The priority queue is needed in order to compare the candidates. So we start the algorithm by essentially with an empty path. So what is an empty path? It's a path that's extended optimally to the target node. So we take this path and we expand it optimally, exactly following the computation of dynamic programming. Then we take the successor at each step. So we say, okay, instead of 1, let's consider 2 for the next iteration. And instead of 10, let's go to 30 here. Why 30? Because it's the successor. So because if you compare 110, 420, and 230, which are the DP weights, 230 is the next best one. So that's the successor. And we do the same for all the steps. And these are our candidates for the next step. Now, these are still partial prefixes. They're not fully expanded, but that's okay. We can put them in the priority queue. We already know their weights because they will be expanded optimally in the same, as we saw, they are deviations. And so in the next step, that's the second iteration, we pop the best one, that's 2 here, and we expand it optimally, we take the successors at every step, and we continue. And that's the algorithm. Now, this algorithm, as I said, it has kind of a long history. It starts from 59, and it has been used in many contexts, like searching for graph patterns, also now conjunctive queries, and there are many references here for you to look at. Now let's go to the second one, which is the recursive algorithm. So the idea of the recursive algorithm is to store the ranking of suffixes and reuse it as much as possible. So what is a suffix? A suffix is a path that starts at any node and it goes to the terminal. So if let's say we focus at this node V here, what we want to do is for V to compute a sequence of sorted suffixes, paths that start from V and go to the terminal. The notation we use here is this pi k of V. This is the kth shortest path from V. So what we want to compute is pi 1 of V, pi 2 of V, pi 3 of V, and so on. So let's see how we do that. For every node V here, we maintain one priority queue and one sorted list. The priority queue will always have size order n, and every entry is associated with one of its outgoing edges, 10, 20, 30. In the beginning, it is initialized with the best possible path from its children. So it's the path that starts with V and continues with pi 1, the best one, from 10, and the best one from 20, best one from 30. The sorted list will be used to store the ordering of the suffixes as we compute them. So this list will keep growing as the enumeration continues. And it can reach, in the worst case, it can reach this n to the power of L size. So how does it work? Well, we pop, to start the enumeration, we pop from the priority queue, and that's the best path from V. So what is it? It's, in this example, a path that goes to the child 10, and it continues optimally from there. It's the pi 1 of 10. That's the best one. Let's store it in our sorted list, and let's continue. To continue, we replace the path in the priority queue with the next best suffix from 10, which is pi2 of 10. And how do we know what pi2 of 10 is? Well, we compute it recursively in exactly the same way that I'm showing you for node V. And we can continue doing this. We pop, to find the second best one, we pop, we store whatever we find in the sorted list, we compute recursively the next best one. Well, for our example, there's no next best one from 30, and we continue. Now, the strength of this method, its advantage, is that when that you can have different prefixes coming to node V and asking for the same suffix. So in our example, we have 1 and 2, and they both come to V, and at some point they will both ask for pi2 of V. And if we store it here in the sorted list, then we can return it immediately when 2 asks for it. And that's the strength of the method, this reusage of the ordering of suffixes. And like the previous method, this one also has a long history, and which is interesting. And now let's move on to the combination of the two, essentially. Now we will think about how can we combine these two algorithms and come up with this Anyk-Part plus algorithm. So as we said, the recursive one can be faster than sorting because it reuses this computation. And for a Cartesian product, it's actually faster both than Anyk-Part and also than generic sorting, because sorting here, if you do the calculation, it has this product, and Anyk-Rec, we can show this has a plus, so it's even asymptotically faster. And that's possible because, as we said, I also explained this in the introduction, it's by reusing comparisons. The fact that we compare here two suffixes S1 and S2 and reuse this comparison for different prefixes P1 and P2. But the recursive algorithm is not the best because in general it has a worse time to k than the partitioning one. And the reason is that this, the way it operates is very expensive. It manages many small priority queues, and in every iteration it has to pop many times from these order n priority queues, and that's why it's slower in general. So to do better, we start with the other one, the partitioning algorithm, and we try now to inject this property of the suffix reuse. And the result, as we said, is an algorithm that is asymptotically better than both of them. Now, one issue with this is that when we try to apply this idea is that the partitioning algorithm doesn't directly have access to the order of suffixes as easily as the recursive one. But what we can do is we can monitor the output of the global priority queue that the algorithm has, and we can infer the ranking of suffixes from there. So what we do is, let's say at some iteration I, we pop this path V1 to V6, and we can break it up into every possible point and get a prefix and a suffix. Now, the suffix, we can go ahead and store it in a sorted list so that we can reuse it later. Then in later iterations, let's say J and K, they don't have to be consecutive, but some later iteration, let's say we see the same prefix again here, V1, V2, V3, with a different suffix, V4 prime, V5 prime, V6 prime. So what we can do is take the suffix and continue storing it in the sorted list. And that's how we can find the order of the suffixes. And now we can use it. So how do we use it? Let's say we know the order of the suffixes. We can reduce it to skip a large part of the successor taking phase of the algorithm. And when we do this, it drastically decreases the size of the priority queue. In the beginning, for Anyk-Part, it's the size of the priority queue depends on k. So if k grows a lot, the size of the priority queue can grow very big. But now with our Anyk-Part plus, the size of the priority queue is bounded by n times L, which is linear. So here's how it works. let's say we pop this v1, v2 at some iteration. As we said before, we expand it optimally, and we start taking successors as before. But let's say at some point at v3 here, we know we look up our sorted lists, and we find that we know the next best suffix from this node v3, and let's say this is s. So what do? We skip the successors for all this part, and we just push to the priority queue the prefix v1 to v3 together with this suffix s. Now, let's return to our previous example and see a bit how it works. Now, I would like to point out that there are some more technical details of how to make this idea work, and I'm not explaining everything in this talk, but I really urge you to look at our paper and find more details. But here's an example to get a feel for it. This is the first iteration of the algorithm, and it's exactly the same as any key part. So nothing changes here. We pop this prefix, we expand it, and then we take the successors as before. Now let's move on to the second iteration, where there is a difference. When we pop the second best one, which is the prefix starting from 2, we expand it optimally, and then we realize that when we visit this node here, as we traverse the path, we realize that we have been here before. We were here before in the previous iteration when we visited from 1, and so we don't have to continue taking successors, and we simply subscribe to this node in order to get the next best suffix. Now, what do I mean by subscribe? There is an intricate detail here, which is that the suffix, the next best suffix hasn't been computed yet, but we know it will be computed before we need it. So essentially, we subscribe the prefix 2 to this node, and the prefix waits until the suffix becomes ready. So let's move on to the third iteration. Now, remember that 2 is still waiting here to get the next best suffix, and we pop here 130, which follows this path here. And when we look at this path, we realize this is the next best suffix. The next best one is 3200. So at this point, we know what the next best one is. We give it to the prefix 2, and we push 2 together with this suffix to the priority. And that's how the algorithm is able to reuse the order of the suffixes. So now the question is, does this always work? In order for these algorithms to work, the ranking function needs to have certain properties, and we call these properties, there are certain kinds of monotonicity. In the literature, many of you might be familiar with Fagen's threshold algorithm, which uses a particular kind of monotonicity. This monotonicity says that if I have an aggregate function and I replace some entry xi with xi prime, and xi prime is bigger than xi, then the result of the aggregate function will also be bigger. Now, this type of monotonicity is not enough for us, because we also need to compare partial solutions. This definition doesn't say anything about partial solutions, essentially prefixes and suffixes. So we need another kind of monotonicity, which we call here subset monotonicity. This definition was also used in the earlier paper that I mentioned, that applied the Lawler-Murty procedure in this kind of default way. And what this says essentially is that if you have a prefix that goes to a node and two suffixes S1 and S2, and you compare the suffixes, and S1 is smaller here than S2, then by combining S1 and S2 with P, you can infer the order between them. And the difference with the previous definition is that here P, S1, and S2 are essentially sets or multisets. And this is exactly the property that dynamic programming needs. And because it needs to compare these partial solutions. Now, for our new algorithm, Anyk-Part plus, we actually need something stronger. We need a property that we call strong subset monotonicity. And the idea is that we need to be able to do what the algorithm does, which is from complete solutions to be able to infer the ordering of partial solutions, of suffixes. So here, we're basically saying that if we visit a node with two different prefixes, P1 and the P2, and we compare P1S1 with P1S2, that's enough to infer the ranking of the suffixes P2S1, P2S2, which is a different prefix. And that's a stronger property. And if we look now at this hierarchy, we have the monotonicity of the threshold algorithm at the top, and this includes cases such as the median for aggregate functions, which we cannot handle with Anyk or dynamic programming. Then subset monotonicity is enough for the first two algorithms, the Anyk-Part, Anyk-Rec, and this includes basically all these cases, sum of weights, min max, or this mean times, basically any commutative selective dioid that Wolfgang was talking about. But now the new algorithm, Anyk-Part plus, requires the strong subset monotonicity property, which here it doesn't apply for this particular ranking function. And what does this say? This says basically that every input tuple has a weight. In order to aggregate those, we multiply them, and then we look for the minimum one. And all the weights are in the 0, 1 real numbers. The problem with this ranking function here is that we will basically start by enumerating zeros. All the winners will have 0 weight, and we can't distinguish between better and worse suffixes, and that's where the algorithm fails. So to wrap up, I will show you some experimental results. And so here we have, in these experiments, we have time on the x-axis, the number of returned answers on the y-axis, and we can see the red line is the sorting, essentially. They produce all the join answers and then sort them. It takes approximately 6 seconds. And if you run this query on Postgres, it takes 11 seconds. On the other hand, the Anyk algorithms start returning answers very quickly after 0.02 seconds. Here you get the best one. And you can see that indeed the recursive one here is faster than sorting by more than a second here. The other two are not faster than sorting, but you can see that the part plus algorithm is in between both of them. And in fact, if now you run a longer query where there are more opportunities for reusing computation, if you have more tables, then you can see that basically Anyk-Part plus is very close to what the recursive one does. So it has, because it exploits the same property. Now, that tells only part of the story, because in these figures, we're basically looking at what happens when the number of returned answers is very big, in the 10 millions here. So now if we look at what happens for smaller k, what happens is that the partitioning variants are faster than the recursive one. And you can see that the recursive one catches up at some point and overtakes them. Now the new algorithm, Anyk-Part plus, can also be better in the beginning if there are enough opportunities for reusing the order of suffixes, essentially. And you can see here, this is an experiment on a real world network or from Bitcoin. And here the part plus variant is indeed faster than both of them. And so as a summary, we saw different NK algorithms, which, if you have a full conjunctive query with a path structure, the complexity in data complexity, it's n plus k log k, which is only logarithmically more expensive than unranked enumeration. We talked about this new algorithm that achieves basically the best known guarantee. And I did not cover in this talk details about how to handle tree structured queries or cycles, but you can also look at our paper for that. And for projections, as I said, actually I didn't mention it, but for free, the n plus k log k guarantee extends also to free connex queries. And as I mentioned before, if you have arbitrary projections, not a free connex query, the best that's known is linear delay and linear preprocessing from this first paper. And I should also mention that our NK algorithms apply not just to queries, but any DP problem, such as the longest common subsequence that Wolfgang talked about, because all of these problems can be represented in this, have this graph representation where our algorithms can directly apply to. And now we will move on with Mirek, who will talk a bit about further aspects of factorization.